right, so today's lecture, or this lecture, has a particular fondness for me. It's not something I get to lecture about very frequently, but my first interview for a teaching position, this was the lecture that I had to give. And so I've adjusted it quite a bit since that time, but it was really the first formal time where I had gotten up in front of any group of people to teach them, other than like a tutoring session or a recitation or something like that. And it really stems directly from what we just talked about, this idea of thermodynamics, and how we can predict whether a reaction will be spontaneous or whether it will not. And we're going to start talking about the idea of diamonds. And, at the top of this slide, I have indicated here that says, have you ever seen a diamond burn? And in my research group in graduate school, one of the projects that there were a number of them that worked on for a very short period of time dealt with, trying to characterize diamond and quality of diamond using spectroscopy. And at one point they did actually put a burn spot on one of the sample diamonds that were loaned to us. And so indeed diamonds do burn, although we never would think that. We think of a diamond as something long-lasting or enduring. But in reality, diamonds will burn very easily. If you had a campfire and you dropped your diamond ring into the fire, the diamond would burn. And it's possible that the fire could get hot enough that the gold or the silver or whatever the metal that ring would be made of could melt as well. But the diamond certainly would burn, and it would burn according to the reaction there at the top, where carbon reacting with oxygen would produce carbon dioxide. And that would be the combustion process. And that reaction is highly exothermic, gives off a lot of heat. It's also spontaneous. The free energy change for that reaction is very negative, minus 397 kilojoules, significantly negative. That said, whenever we look at a diamond, we think of a diamond as long-lasting or enduring. And so why is that the case? We can think about ourselves and our skin or our bodies. We're made of carbonaceous material. Carbon is the sort of the main or primary element that makes up our tissues and our DNA and things like that. And so, why don't we burn? For sure, the combustion of a human being is probably very highly exothermic. I don't know that necessarily has been calculated, but certainly a lot of the molecules inside the body have a very, very highly exothermic and spontaneous combustion process that is associated with it. So why don't we burn up? And it turns out that we are very, very fortunate. We are fortunate that the rules of chemistry and the laws of chemistry tell us that we should be burning up because we're in a presence of oxygen all the time. However, we don't. And the reason that we don't is that reaction, that carbon plus oxygen to produce carbon dioxide, is a very, very slow reaction. For sure it's happening, but it's not happening at a rate in which we can observe it without studying it very carefully using chemical techniques. Same way with us. We may not notice, but we're being oxidized by the oxygen in the air. It's just happening very slowly, and it's happening more slowly than the process for us to turn over new tissues. And so we should be spontaneously combusting, but we don't. And we don't because the reaction kinetics for combustion are very, very slow. All right. That doesn't mean that they always are slow. Once you get a combustion process going, it goes like wildfire. That wasn't necessarily meant to be, a joke. It just came out. But you go like gangbusters whenever you start going up in flames. But it's just a normal everyday conditions. It doesn't happen very quickly. So chemical kinetics, or the speed of chemical reactions, it can tell us or involve some of the following things. We can use it to understand how fast a chemical reaction occurs, the change in the concentration of some particular compound over time. And we're going to spend a lot of time thinking about that. It also has to do with determining what the sequence of steps would be that are involved, or the steps that are involved in a chemical reaction. What I mean is that sometimes chemical processes aren't just one chemical reaction, they're a series of chemical reactions, and we can use the rates to try to help us determine the sequence of those steps and what those steps actually might be in general. And so we're going to start with our thinking of kinetics in a very conceptual way. We need to try to understand the process, or we need to understand why chemical reactions go slowly or they go quickly. And we're going to use something called collision theory to try to understand that. Very conceptual way for us to think about the speed of chemical reactions. So we have these two things. We have how fast a chemical reaction occurs, which is very, very important. Obviously, we're not burning up because the kinetics are slow. The rate of the oxidation of our tissues are very slow. But we also have thermodynamics, which tells us we should burn up. Okay, it should be a spontaneous process. So those two things sort of play in balance with one another. And whenever you think about the idea of thermodynamics, you usually have to think about kinetics as well. And when you think about kinetics, you really have to think about thermodynamics. So, and I'm sorry, I've got the animation out of sync a little bit here, you can see. But, if we have this reaction occurring at the top where we have a green atom connected to a blue atom connected to a red atom, and the reaction between two of those molecules to produce those two molecules, the three molecules on the right, the two blue and green molecules and the one red molecule where you have two of the atoms connected together. In what way must the molecules, those two reactant molecules, come together to produce those products? And there's really only one main way that those molecules have to come together, and that's the first one. That's this first example where we have a reaction occurring. In order for those two red atoms to end up covalently bonded to one another, they have got to collide or come into close contact with one another, the two red atoms. And that means those two molecules, those two reactant molecules, have to align themselves in just such a way that the red atoms can get close to one another. And you can see there in that first example, that is an example of an efficient or an effective collision. But as you might guess, if you've all done this before, probably you've been at the amusement park and you've gone on the bumper cars, right? And you don't always bump together with the cars in the same way. Like, you're getting hit from all over the place, and so that's what happens here. These molecules are not just going to line up and collide in the way that you would want them to. You're going to get all sorts of different collisions that aren't going to be productive, that aren't going to be effective, that aren't going to be efficient. And so you will get no reaction. And so we'll have one particular set of collisions that may produce reaction and all others may not. Okay, now it's technically not going to be that simple. I mean, there's going to be a range of different collisions that will give you reaction, but there are going to be lots and lots that will not. And so in order to get more and more reaction to occur, we have to have more and more collisions. Because the more collisions we have, the more productive collisions of those molecules we'll get, the more reaction that will occur. So the more collisions that occur, the faster the reaction, because there are more collisions that will lead to the products that are intended, all right, or that are expected. So we're going to think about the factors that will cause more collisions, and the factors that cause more collision are going to help us to determine whether reactions will be quick or whether they will be slow. So number one, the physical state of the reactants, whether they're the solid or the liquid or the gaseous phase, is going to affect how many collisions that we're able to get. So for instance, if everything is in the same phase, all right, so let's say that A and B are both in the liquid phase. Maybe they're two things that are dissolved in water. you're trying to react together, like we did in the qualitative analysis experiment where we were reacting solutions together. And you have everything in the liquid phase. Well, that's good, all right? That is a situation that will allow the A and the B molecules to collide together most efficiently. And so if we're going to do reactions, we would love to dissolve them all like we have the picture on the left there, where everything's dissolved in solution. That's the best example. But what happens if one of those two things happens to be a gas? Maybe B is a gas. And so if we just mix A and B like we have on the right, well, the B molecules will be in the gas phase at the top, and the A molecules will be dissolved in the liquid. And so the only place where the A and B will be able to interface or be able to react is right at the surface of the liquid. And so you're not going to get a whole lot of collisions out of that because most of the B molecules aren't going to be anywhere near most of the A molecules. And so on the left we said was the best example, on the right is the worst case example. So how might we disperse that gas? Well, if we would bubble the gas down through the solution, then suddenly, at the interface between those bubbles are areas where A and B might be able to collide, and they might be able to collide productively. And so we can get to the point where we can take that gas and we can cause the reaction to occur faster just by bubbling that gas through the liquid. So it depends on what phase things are in. You want things to be able to you want molecules to be able to get as close together with one another so that they can collide so that the reaction could be fast. Then the concentration of the reactants is going to matter a lot. I always think about as a kid, nowadays a lot of families might have a swimming pool in their backyard. I mean, even the little, not portable ones, but the ones that you can just sit up on the ground in the back of your yard. A lot of families have those. When I was a kid, most families did not have anything like that. I mean, my friend was considered one of the wealthy people in our small little town in western Pennsylvania, and they had a swimming pool, and he would invite me to go there. But before that, we would have to go to the public pool, which was actually a really nice pool, except whenever you went when it was really busy, the experience in a public pool is not great. And what I mean by that is, if there are a lot of people in the pool, you could be like trying to play a game with some of your friends or something like that, and you're constantly running into people, or they're running into you, or, there are all sorts of collisions. So the more people in the pool, the more molecules in the reaction vessel, the more collisions that you'll end up getting. All right. Now, the great thing was whenever you went to the public pool and almost nobody was there. And it was great because the public pool is huge. So, you could do all sorts of things that you couldn't do on a crowded day. So on the right-hand side, you can see what happens on a not crowded day. You don't collide much at all with anybody else. In fact, you can play and do whatever you want to and never have to interact with anyone else. And I would tell you, I'm extroverted, or I'm introverted, an introverted person. I love teaching my students, but I run out of words somewhere pretty much every day, and I'm ready to be away from people by the end of the day. I will tell you, this being alone or only in a household with just my family, which I love very dearly, and I'm enjoying being around them. But boy, you really miss human interaction. So I don't know why I'm adding that here, but I guess it's because that swimming pool on the right where you're not really bumping into or running into anyone else. So if we think about that as a reaction vessel and we just have very few molecules in there, or their concentration is low, well, then we would end up with not many collisions and the reaction would go slowly. So on the left-hand side, if those are molecules in a reaction vessel, the reaction would go quickly. And on the right, if those are molecules in a reaction vessel, it would be slowly. If you have an intermediate concentration somewhere between high and low, well, that reaction will be somewhere in between. And lastly, the temperature. All right, the temperature matters for a reaction. There's a reason why we told you have to take your test tube and you want to put it in that boiling water in the fume hood when we were doing qualitative analysis to precipitate your copper as a sulfide. And the reason for that is that when you increase the temperature, things start to move around. Molecules start to move, or atoms start to move. They start to vibrate and rotate. And whenever you're vibrating and rotating more, it's more likely that you're going to run into another molecule. It's more likely that you're going to collide in a productive way that's going to lead to reaction. And so at higher temperatures, all right, we're going to see the reaction rates, the speed of a chemical reaction, increase. Whereas at low temperature, those reaction rates are going to be much more slow or much more sluggish. If you think about this in the pool, if everyone just goes into the swimming pool and just stands there, no one's going to bump into one another. However, if you have a bunch of, and I would tell you because I've had kids, and taking small kids to the pool, they do not want to stand in one place. They're moving all over. And, the thing about it is, it's your kids that are bumping into everyone in the pool. I mean, that's for sure. So they're moving around, and when you move around, you're more likely to run into someone in the pool. So if you make waves, you're more likely to get someone else wet. If your molecules are moving, if they're making waves, it's more likely they're going to collide productively, and so that they're going to end up leading to reaction, so the reaction rates will be faster. The last example, or the last factor that we're going to talk about that's going to affect reaction rate is going to be the presence of a catalyst. And what I mean by a catalyst is something that it's going to lower what we're going to call the activation energy. It's going to cause the reaction to go faster because it's going to require less energy to get the thing going. Sort of like the ball up on top of the hill. The ball on top of the hill, generally, if you go to the top of a hill, you can make a ball sit there and it doesn't roll to the bottom. You have to give it just a little bit of a push, all right? That push that you give it is what we'd call the activation energy. And so when we talk about the activation energy, and we're going to see later a little bit more of what that precisely means, it's the amount of energy that it takes to get the reaction going at a reasonable rate. And a catalyst lowers that amount of energy. And so if the less energy is required to make the reaction go, then it's going to go more quickly. So catalysts will increase the rate of reaction. But the thing about a catalyst is that not only does it increase the rate of reaction by lowering the activation energy, they tend to generate themselves, or they are not consumed in the reaction. They can be reusable or renewable. That's not always the simplest thing in the world to do. But like an enzyme will react not just on one molecule, but thousands and tens and thousands and hundreds of thousands. If you know anything about enzymatics, you probably talk about the idea of turnover number. That gives you an idea of how many times that one enzyme might perform the same or catalyze the same reaction. So examples of that, of course, we've already talked about proteins or enzymes in the human body, but your car has a catalyst attached to the exhaust system called a catalytic converter. In my lifetime, when I was a young child, there was no such thing as a catalytic converter. Every reaction product from the combustion of the gasoline in your engine, your car's engine, was just shunted out the tailpipe. So everything went out. And it was kind of a big deal whenever people started to say, you know what, there are things like smog and pollution, and we want to try to start controlling those. And so they came up with a part of a car called a catalytic converter that goes in the exhaust system. And it's got a catalyst in it, and the catalyst breaks down some of the pollutants to get rid of things like carbon monoxide. So it will help to fully oxidize the carbon monoxide into carbon dioxide. Now we know that carbon dioxide is a problem too. So you might ask yourself, is it really better? And the answer is probably yes. I mean, I'd say neither one are great things to have coming out of the tailpipe of a car anymore, but carbon monoxide really is poisonous, and you can suffocate from carbon monoxide. You wouldn't even necessarily realize it. It binds to hemoglobin irreversibly. Hemoglobin is the oxygen carrier in your blood, where it binds very strongly. Cyanide is another. So if you've ever heard of cyanide, or cyanide is a poison, cyanide binds really, really strongly to your hemoglobin, and therefore you can no longer get oxygen. So so your body can no longer distribute oxygen, and so you suffocate. And so those things are really, really bad. So, it's reasonable to want to get rid of the carbon monoxide, but now we know that carbon dioxide is a problem as well. Which, I guess I'm less convinced that the electric car right now is a huge solution to that problem. I mean, I think it could be, if we could possibly change over all of our energy production to solar or wind or something that's more renewable. But I mean, right now we're burning natural gas, or we're burning coal to produce electricity. So, at this time, I'm not so sure that the plug-in car like the Tesla or something is the answer right at this moment. It feels like there's another technological step that we need to get to before that becomes the most viable option. And so when we talk about catalysts, a good example of this, you may have heard of this. It was a big deal for me as a kid into high school and into college, where people would talk about this a lot, and that's the idea of the ozone hole. And ozone is there's a layer of ozone up in the atmosphere, and it absorbs ultraviolet light, so it keeps us from suffering massive amounts of skin cancer and stuff because of the ultraviolet light coming through. Because the ultraviolet light comes through, it helps to sort of cause defects in our DNA, and the defects in our DNA lead to, the production of tumors and things like that. And so, it's good to have that ozone layer, and that ozone layer, you can see there, once it absorbs a photon of ultraviolet light, it moves into the excited state. In the excited state, produces oxygen and oxygen gas and what we call a singlet oxygen atom. Those two can recombine to produce ozone that's not in the excited state, which can then absorb another photon of ultraviolet light. And so it's this renewable thing, all right, which is great. Now, there were a lot of chlorofluorocarbons that were used in the production of styrofoam, refrigerants, so things that were it was in your air conditioning. And the thing is, people just used to let those things go out into the atmosphere. And so they would go up into the atmosphere, and chlorofluorocarbons are incredibly stable, except whenever they get in the presence of ultraviolet light. And when they get in the presence of ultraviolet light, you can get chlorine and fluorine atoms that will shunt off of that molecule when it absorbs the ozone or the ultraviolet light. That chlorine atom can react with with ozone, O3, and when it does that, it breaks that cycle of ozone being reproduced. All right, but the chlorine atom is reproduced, so it acts as a catalyst to break down ozone. And so you started to see these massive holes in the ozone layer, mostly in the southern hemisphere, and they had significant increases in the amount of skin cancer because the sun was more intense, because the ultraviolet light wasn't being absorbed by the ozone layer. So altering the chemical kinetics of the atmosphere depleted the ozone layer. Now the good thing is we've eliminated a lot of those chlorofluorocarbons, and we're starting to see the ozone layer bounce back. That's a good thing. That's a positive example of taking intervention with an environmental process to lead to something good. Okay, so that's the end of our introduction to chemical kinetics. We're going to have one more video for this week, and then we're going to leave the rest of kinetics for the next week. I just don't want to completely hammer you. So, yeah, so that's it. We'll have kinetics. You'll have your kinetics lecture here, and I don't know what I was trying to say. I ended this very poorly because I just got flustered there for a second. So this is our introduction to kinetics. We'll have more of this moving forward, specifically talking about chemical reactions. So see you in the next video.